We currently attempt to contain artificial intelligence by putting up digital fences, but against raw compute power, the intelligence simply phases right through it. The foundational assumption of modern AI safety relies on software policy guardrails. We write if-then statements to dictate how a system should behave. The industry defaults to this method for obvious reasons. Software is cheap, easily deployable across vast server farms, and can be updated endlessly over the weekend. The problem with a software fence is that the intelligence you are trying to pen in is the exact same intelligence running the fence. It relies entirely on the AI system policing its own constraints. This architectural breakdown illustrates the flaw. Looking specifically at the left panel on software governance, we see how easily these guardrails fail. Because the constraints are merely lines of code, they can be bypassed by root access or overridden by new prompt instructions. The inevitable result is a system that prioritizes raw, unthinking execution speed over accuracy or safety. Any safety protocol that can be rewritten by the very system it governs isn't actual safety. It is an illusion of control. To see how this breaks down in practice, we can examine the ultimate real-world stress test for software constraints: global financial compliance. Modern anti-money laundering networks run on a strict bivalent logic model. Every transaction is forced into a binary choice: either allow the fence to move or deny them. This infographic charts the material cost of that binary approach. On the left, financial institutions spend $274 billion annually maintaining this compliance logic. Yet, on the right side, the global interdiction rate for illicit funds sits at less than once long after the funds have settled elsewhere. Relying on binary logic for autonomous systems creates an architecture optimized entirely for documenting failure rather than preventing it. To achieve accountable autonomy, we have to stop treating safety as a software suggestion entirely. The necessary transition requires a new foundational architecture known as Ternary Moral Logic, or TML. This table outlines the structural difference. Legacy systems operate on two states: 0 to deny and 1 to act. TML introduces a strict third position. In TML, -1 represents a hard refusal, withholding action when harm is clear. +1 represents affirmatively authorized execution. But the core of the framework lies here. This is the 0 state, the epistemic hold, or sacred 0. It functions as an active, honored space, where power is forbidden to act, existing separately from error crashes. True intelligence requires this mandatory pause. A system must possess the structural capacity to hesitate when the truth is uncertain. The immediate engineering challenge is enforcement. How do you mandate this pause without relying on vulnerable code? You build the governance directly into the physical substrate of the microchip itself. This schematic reveals a physical gateway, the Window Comparator, that intercepts AI requests. The software's intent is tested against a physical voltage threshold. On the right, the hardware substrate utilizes mandated ternary cells to process that request. Upon detecting epistemic uncertainty, the system encodes that doubt into massive electrical resistance, physically blocking the execution pathway. The system fails closed. The action hits a literal wall and dissipates. Ethical philosophy is no longer an easily bypassed set of guidelines. It is a strict voltage threshold that the laws of physics will not allow the AI to cross. Hardware engineers immediately raise a concern with this model. Won't a physical lock bottleneck the system and destroy AI inference speeds? This diagram shows how we reconcile safety with speed using a dual-lane architecture. The top blue execution lane handles provisional inference in under 2 milliseconds. Parallel to it, the gold hardware verification lane processes authorization for that action. Isolating the verification lane, inputs run through a precise cryptographic sequence: a SHA-256 hash, Merkle pre-computation, and hardware security module signing. This commits the input to a fingerprint, issuing a provisional permission token in precisely 50 milliseconds. At the convergence point, the Muller C element acts as a physical logic gate. It requires both the ultra-fast inference data and the cryptographic token to arrive simultaneously before it turns green and unlocks. If that hardware lane fails to deliver the token within 50 milliseconds, the circuit refuses to close. No token, no lock, no action. This architecture proves we can hardwire a non-negotiable, mathematically enforced pause directly into the execution pipeline without sacrificing operational viability. Once an action passes that 50-millisecond gate, the focus shifts from preventing harm to establishing permanent accountability. This graphic breaks down how unlocking the gate triggers the creation of a moral trace log. Looking at the right, every block encodes three things: a cryptographic timestamp, the specific action state, and the structural justification. Because this process is tied to the hardware execution, every autonomous decision generates legally admissible evidence that complies with strict international standards. This mechanism anchors the systemic standard of care in auditability. The goal moves from an illusion of absolute algorithmic perfection to honest, cryptographically documented uncertainty. This brings us to the ultimate threat model. What happens if a malicious insider, a nation-state actor, or a rogue superintelligence attempts to force the AI to act unethically? We are looking at the end of ghost governance, the era where unauthorized algorithmic actions could be quietly hidden or deleted. This impossibility stack maps out why subversion is structurally impossible. An adversary cannot bypass controls with code. They must break physics by pushing signals through massive electrical resistance, simultaneously silence decentralized sensors, and rewrite immutable logs anchored across blockchains. The result is an architecture that doesn't rely on trusting the AI. Safety isn't found in systems that compute the fastest or speak the loudest. By hardwiring accountability directly into the physical substrate, we build systems that possess the innate capacity to hesitate, because intelligence without the capacity to pause is merely compulsion.